Hi there, friends. It is Ben again, and I've got another one of my thrilling videos. This time, it's a sequel. Remember the one about L'Hopital's rule that was so riveting before? I'm going to blow your mind with the sequel without equal, L'Hopital's rule 2. So the thing we're looking at now is going to be when you have different indeterminate forms. Previously, we had indeterminate forms that were 0 over 0, infinity over infinity, and 0 times infinity. We also did a bonus feature there of infinity minus infinity. But now we're mainly going to be thinking about powers. So here is, here is the statement of what it is we're looking at. We already have L'Hopital's rule in mind. But keep in mind, L'Hopital's rule, we only get to apply it if we've got 0 over 0 or infinity over infinity. So when we have 0 to the 0 power, you know, if you've got a number that's not 0 and you put it to the 0 power, it's automatically 1. But it is possible that you can find ways to have things that are going to 0 in such a way that putting it to the 0 power will cancel out somehow and you don't get 1. I am going to go ahead and be honest with you in saying it is really hard to make up examples where 0 to the 0 becomes anything other than 1. It's just kind of the nature of how the algebra works. I can make them up, but it's hard. So likewise, if you have something that's going to infinity and you've got it to the 0 power, you get it to a power that's going to 0, then it might turn out to be something other than 1 as well. That one, it's a little bit easier to construct stuff, okay? And then the 1 to the infinity sorts of things, it's relatively easy to construct examples for that don't turn out to be 1. You can make them be anything, okay? Now, all of these, when you encounter them, you need to be able to apply L'Hopital's rule. You are definitely not allowed to say, oh, this thing's a little less than 1, therefore this goes to 0 or something like that. It has to be L'Hopital's rule. You have to be using the rules that we've got, okay? As you might guess, lots of people don't want to do that because L'Hopital's rule, it's just hard algebra, you know? You can do it though, all right? All right, so the whole notion is that you're trying to turn it into something where 0 over 0 or infinity over infinity will pop up. And the trick to that in any of these things that are powers is to make use of the fact that the exponential of a logarithm will cancel out and just get you the stuff. I guess really I have stated it the wrong way there. What you need is not that will cancel out and get you the stuff. What you need is that you can take stuff and rewrite it like that, okay? And I do not know where that symbol came in, all right? And yeah, okay. So, and, oh, there it is. Okay, so the easiest example to see is if you've got x to the x, that you can just rewrite that as e to the log of x to the x. And then your logarithm has a special rule that you can take a power and pull it out. So that becomes e to the x log x. Now, as x is going to 0, that becomes 0 times negative infinity. It's a 0 times infinity case. And once you have that, we looked at before how you turn 0 times infinity into a 0 over 0 or an infinity over infinity. So that's where we're going on these. Oh, I know that means that you have to kind of build on stuff that was already hard to do with something else. But yeah, that's the nature of the beast. So let's see what we can do. All right, this first one here, we've got the limit as x is going to 0 of cosine x to the power 1 over x squared. So what we have to do is off to the side say, as x goes to 0, cosine x is 1. And then the 1 over x squared, that would be going to infinity. So I have a 1 to the infinity indeterminate form. So don't write L'Hopital's rule yet, because remember L'Hopital's rule means we're doing that derivatives thing with the top and the bottom. We don't have that yet. We have to add ourselves an extra step here and say this is equal to the limit as x goes to 0 of the cosine x, so e to the log of the cosine x to the 1 over x squared power, which is going to be equal to the limit as x goes to 0 of e to the 1 over x squared power, or 1 over x squared, log of the cosine of x. Now, notice that we're going to do that every time on one of these power things. So really, you should be thinking about skipping straight from here to here, because you're going to be using the same technique every time on it. And then we can say equals limit as x goes to 0 of e to the log cosine x divided by x squared. Okay. Now, if we think about that and think about plugging in, as x goes to 0, cosine x is going to go to 1. So we've got a log of 1, and we've got then a 0. On the bottom, we've got something that is going to 0 the whole time. So we can see we've got a 0 over 0 case, right? Now, bear in mind, this is just a little scratch notes out to the side for us to figure that out. We're not actually saying it's equal to those numbers, because those are not numbers. Those are just kind of ideas. Once we found out that it's a 0 over 0, though, we can go ahead and say, use L'Hopital's rule with 0 over 0 case. The limit x is going to 0. We still have the e there, but now we have to take the derivative of the top and the bottom. So the derivative of the top, you've got a logarithm, so you're going to have 1 over the cosine x. So derivative of a logarithm is always 1 over whatever was inside the logarithm. But then the chain rule says we have to take the derivative of logarithm, which is minus the derivative of cosine, which is minus sine x, divided by, now the derivative of x squared is 2x. So we'll want to get that to looking better using our algebra, and we'll still have the e. So that is really a minus tangent x there, but I'm going to rearrange it slightly differently. I'm going to write 1 over 2 cosine x, and I'm going to put the minus 1 over 2 cosine x, and then I'm going to write sine x over x. Do you see why? Sine x over x we know goes to 1. And so I just lumped everything that wasn't that sine x over x into one piece, and I know I can actually evaluate those. So as I plug in the 0 for the x, cosine of 0 is 1. And so I have e to the minus 1/2 times sine x over x goes to 1. So I have e to the minus 1/2. If you'd like, you could also write that as 1 over the square root of e. It's fine to write it as e to the minus 1/2, okay? But if you like to see the square roots and stuff, then yeah. If you need a number for that, you can put that in a calculator and approximate, but that is not what I want for an answer. On these limits, I don't really care what it's close to. I want to know what it is. And that probably is a super weird philosophical sort of thing to say. So, sorry. All right, here we go with another one. So this time, x is going to 0 from the right. On the previous one, look back there, we didn't have that sort of thing coming out. Cosine of x was our base, and we knew that that was going to be close to 1. And when we have our base being close to 0, we have to worry about coming from the left or the right. Because if you put a negative number to a fractional power, it does not exist, at least not as a real number. When you talk about negative numbers being put to fractional powers, you have to bring into account I, the square root of -1. And as soon as you do that, everything gets really complicated. We don't try to do that in here, okay? All right, so with tackling this, we've got that limit as x goes to 0 from the right. And, oh, I guess I should have off to the side said x is going to 0, and the tangent of 0 is 0. Okay, so I'm going to come along here and turn this into e to the, I'm going to go direct on it, tangent x times the log of x. See how I just took the log of the base there and then put the tangent out in front of it because the tangent was the power. So since that's going to happen over and over again, we go ahead and try to do that. So once we have that, we know as x goes to 0, tangent x is going to be 0, and the log of x is going to be -infinity. So that's not 0 over 0, but it's kind of getting there. Now we have a choice. We can either do it as as e to the log x divided by cotangent x. That would be 1 over tangent, right? Or we could do it with the 1 over log x and having the tangent on top. We should get the same answer either way. Which one's easier? Total guesswork. I'm sorry to tell you that. If you are less comfortable with the trig functions, maybe you go with putting the log underneath. And so you would have 1 over log x, but then you got to do a lot of chain rule stuff. If you are less comfortable with logarithms, maybe you go ahead and do what I'm doing here. So not saying I'm uncomfortable with logarithms, just saying that that might be a motivation for you to do it this way. I don't know. But now when you plug in the log of 0, is going to infinity, the cotangent of 0, because tangent is going to 0, the cotangent is going to infinity. Now it would be, I believe, positive infinity, okay? But yeah, but we do have infinity over infinity. So L'Hopital's rule, infinity over infinity. Let's see what happens. So we still have the exponential there. And then the top, the derivative of log x is 1 over x. And the bottom, and I'm going to have to kind of scoot it up there a ways because it's, all right, the bottom, you might have to look this one up. The derivative of cotangent is minus cosecant squared of x, okay? Ugh. Now that's got a bunch of fraction stuff in it, so let's try unscrambling it and see if we can just evaluate it at this point. So I'm going to have e to the 1 over x, and I'm going to have the minus here. Cosecant is 1 over sine. So this will turn into sine squared x. Maybe I should have put this over here instead. Okay. And then that's equal to the limit as x goes to 0 from the right, e to the minus. I'm going to try to manipulate it so that I get sine x over x, because I know what that goes to. There's another sign left. So I'll put it out like that. Now when I plug in, I will have e to the negative 1 times 0. That means I have e to the 0, which is 1. Boom, we're done. Okay. That was a pretty hard one, in particular because you had to know the derivative of cotangent to get it there. If you'd done this with 1 over log x and had the tangent on top, then you would have had a secant squared cropping up. And then on the bottom, you would have had like a 1 over, yeah. You would have had a complicated chain rule problem, okay? So this probably was the easiest way to do this, which is saying something, right? Ugh. All right, so let's try this one here out. We're plugging in, quote unquote, infinity. So the log of infinity is still infinity. And then 1 over infinity is going to be 0. So we have the infinity to the 0 power. It's a powers one, so we're going to use the exponential logarithm trick. And this is not L'Hopital's rule yet. And this is just rewriting it. So e to the 1 over x logarithm of x. Well, that's scary. So if we think about what's going on there, the 1 over x is going to 0. The log of x, so the log of infinity still is going to be infinity. So really at that point, you've got a 0 times infinity problem, but it really strongly hints that we should be doing it as log x divided by x. So when you plug in there, you're getting a infinity over infinity sort of thing. So that says we're going to be allowed to use L'Hopital's rule now, finally, with the infinity over infinity case, because we checked. Limit as x goes to infinity, e to the power. Now, okay, derivative of a logarithm is 1 over that thing. And then times, you have to take the derivative of the thing that was inside. The derivative of that log x is a 1 over x. Divided by, now we take the derivative of that x down there, and that's just 1. So this is the limit as x goes to infinity, e to the 1 over x log x. Now you've got 1 over infinity. That's not an indeterminate form. As you go to infinity, that is going to be a 0 in your power. So we end up with a 1 coming out of this one. So yay. That's not too bad. Hopefully. Yeah. All right. So let's tackle another one of these. So this one, we would think about plugging in the 0, and we'd see that in the limit, we've got something that's going to 1, and the power is going to infinity, right? So we've got a 1 to the infinity power, 1 to the infinity problem, And anytime we've got one of these power things, we're always rewriting limit x goes to 0, e to the, and now we're going to take the logarithm of that stuff there. You'll have a 1 over x squared logarithm of sine x over x. Okay. So if we plug in at that point, you can see that we're going to have an infinity times a log of 1, so a 0. Okay. Now, this particular time, it suggests that the way to get it into 0 over 0 or infinity over infinity is to just write it as log of sine x over x and then divided by x squared. Now, I know you're eager to jump in on that and say, aha, I have something now where I have 0 over 0. I'm going to go do L'Hopital's rule. But I'm here to tell you, you want to be a little cautious on that and make sure not to work too hard. Remember, I'm on your side on these things. I don't want to work too hard either. Okay, so I forgot to write my e. So e to the power this mess. Now, what on earth motivated me to do that? Well, motivation is going to be a little bit murky, but what allowed me to do it is that the log rules about division just turns it into a subtraction. The motivation is that when I take the derivative of log x, that's just 1 over x. But when I take the derivative of the log of the sine divided by x, I have to do the derivative of a logarithm, and then I have to do the chain rule, which leads me to do the quotient rule. And oh my gosh, it's a mess. I think this is going to make it just one step easier. Not to say it's going to be easy, just one step, maybe one step less hard would be the better way to put it. All right, we'll do the limit as x goes to 0, e to the power. And now we have to think about derivative of log is 1 over the sine. And the chain rule says times the derivative of sine, which is cosine, minus 1 over x. And downstairs, we have 2x, right? So then if we simplify, oh, I forgot to write something. L'Hopital's rule. What kind was it? 0 over 0? Yeah, okay. All right, so now we're going to say e to the, okay, that would be cotangent x over 2x minus 1 over 2x squared. Okay, so as x goes to 0, cotangent x goes to infinity. When you divide it by 2x, we're still going to be thinking about this going to infinity, and then minus something going to infinity. All right, I think that didn't help too much, right? I think we're going to have to see what's going on here, because if you look at the way I wrote it, that's going to turn it into infinity minus infinity. So let's try stepping back a little bit there. Let's not rewrite it quite that nice or quite that way. Let's see if we can rewrite it as just cotangent x minus the 1 over x divided by 2x, and we'll just see what happens then. So as you plug in, the x is going to 0. The cotangent x minus 1 over x, oh gosh, that's still infinity over, or that's still infinity minus infinity, isn't it? Oh. Okay. So I'm going to hope that what we've got there on the top is 0. And the thing that's on the bottom is definitely 0. I'm going to try L'Hopital's rule again with the 0 over 0 case, and let's see what happens. So we still got the E, derivative of cotangent. What is that? That is negative cotangent x cosecant x. And now this will be minus 1 over x squared. And then all this stuff down here is just a 2. Okay, well, I think this may have made it better, right? So if you think about cotangent x, that is, I'm going to draw a brief little graph here. Cotangent x goes to positive or negative infinity there, okay? And so does cosecant x. And they go to the same infinity. So because these two things that we're looking at here are both going to plus infinity or both going to minus infinity, according to whether your x is positive or negative, then that suggests that this thing here is going to positive infinity, because if it's two negatives, the negatives cancel. But positive infinity, and then a negative out in front of it. So we've got a negative infinity minus another infinity. So we're getting something out of this that is minus infinity. So we'll write equals, and then maybe out to the side we write to ourselves, we're getting e to the minus infinity. But e to the minus infinity is going to be 0. Okay. So that was kind of some tough reasoning too, but you know. All right, let's tackle another one. So with this one, if you're like me, that cosine 1 over x squared kind of scares you, because as x is going to 0, cosine 1 over x squared means you get something that oscillates, and it's just a mess. But we're not doing x going to 0, we're doing x going to infinity. So as x is going to infinity, that cosine is turning into a cosine of 0, which is 1. And as x is going to infinity, of course, the x to the 4th is going to the infinity power. So we get a 1 to the infinity type problem. So let's rewrite it as limit as x is going to infinity, e to the x to the 4th logarithm cosine 1 over x squared. That's going to be a mess to write. Let me write cosine of x to the minus 2. All right, that'll be easier just to see later. So the cosine, the x to the minus 2 is going to 0. The cosine then is going to 1, and then the log is going to 0. So that means your x to the 4th log stuff, that you've got an infinity times a 0 there, right? Now, God, this is, I think, going to be least awful if we put it as a logarithm of the cosine of the x to the minus 2 over the x to the minus 4. Okay, I think that's our least offensive version of this one. Okay, so if we try plugging in the infinity there on the top, your cosine of, your x to the minus 2 will turn into a 0, your cosine will turn into a 1, your log will turn into a 0. Great. Your x to the minus 4 that's on the bottom will turn into a 0. Awesome. We have 0 over 0. We are allowed to use L'Hopital's rule in the 0 over 0 case. Okay. Limit x is still going to infinity. We've still got an e. All right, the top has a logarithm. So we will have 1 over all that junk times. Now the derivative of the thing inside is a cosine. So we will have a negative sign with an x to the minus 2 still hanging inside there. And then the chain rule says we have to take the derivative of that, and we'll end up with a minus 2 x to the minus 3. All that divided by minus 4 x to the minus 5. This does not look good. But let's see what we can do. We can group those things together and talk about a tangent. And maybe we can put these together. And do notice we've got 1, 2, 3 negatives that are floating around there. So equals limit x is going to infinity, e to the power negative, because 3 negatives, you get some cancellation, tangent of x to the minus 2, okay, and then times, let's see, if you do some cancellation there, you should have 2 remaining on top, x to the 5th, and then an x to the 3rd there, okay? And then we can go ahead and do some more cancellation and have an x squared. So this is limit x is going to infinity, negative, now, e to the negative tangent of x to the minus 2 times 2x squared. Goodness, that's still got us with a 0 times infinity type problem, right? Okay, I'm going to try one more line of it. No, I'm sorry. I always end up doing this. I'm going to have to add an extra page because it may turn out that this is not that bad, but right now, okay, y'all can't see it, but I have the little beach ball sort of thing. It was taking time to do that. All right, so I'm going to turn that into the limit as x goes to infinity, e to the power, I'll leave the negative here. I think I'm going to leave the tangent of x to the minus 2 on the top, and maybe I'll leave the 2 on top as well, and then have x to the minus 2 on the bottom. Oh my God. I can use L'Hopital's rule again, but I don't actually have to. This is pretty sweet, okay? Limit x is going to infinity, e to the power, and then we're going to go ahead and put the negative 2 here. I'm going to break tangent into sine and cosine, all right? The reason I do that is that leaves me with 1 over the cosine of x to the minus 2 times sine of x to the minus 2 over x to the minus 2, okay? And let me move those around so that they're not cluttering each other up. All right. So the reason I say this is kind of a sweet way for this to come out is that we need to recognize as x is going to infinity, this thing here is a 0 over 0 thing, but it's a special limit with exactly the same thing inside the sign and the denominator. So this part is going to go to 1. Now this x to the minus 2 here is going to 0, and that means that your cosine is going to 1. So this is turning into e to the power minus 2 times 1 times 1. Wow. So this turns out to be e to the minus 2, or if you prefer, 1 over e squared. Okay. That's pretty cool. It was a mess, yeah, but it's pretty cool that it came out to get us one of our special limits. All right. So this is our last one here. Hopefully it does not turn out to be any harder than the previous one. Ugh. Okay. So if we try plugging in our 1, we have to remember that the x is coming to the 1 from the positive side. So when we say something about this 1 over 1 minus x, the x is, well, yeah, I should just draw a quick picture here. So if you've got numbers that are slightly bigger than 1, then you have 1 minus that, so you get negatives out. And so that means that this graph looks kind of like that. Okay. So on this one, when we're plugging in, we have 1 to the power negative infinity, right? So if it had been x is going to 1 from the left, then we would have looked at on this side and said it was going to the positive infinity. In both cases, it's 1 to the infinity. So it's still an indeterminate form, but it might be slightly different as we go along. So like before, we make it into an e, and we're going to have a log x, because the x's are base, and divide by 1 minus x, all right? So when you plug in the 1, you can see that we have a 0 over 0. So that's L'Hopital's rule, and it's in the 0 over 0 case, because we checked. Limit x is going to 1 from the right, e to the power 1 over x, that's the derivative of log x, and 1 minus x, the derivative of that is just minus 1. So that says that we are taking the limit as x goes to 1 from the right of e to the minus 1 over x. Well, that's not an indeterminate form. That is just e to the minus 1, or if you prefer, 1 over e. Yay! So, yeah, that was kind of an anticlimax after having done the previous one, right? But anyway, all of these problems, they're very detailed. You have to be super careful and not drop negative signs. And often you have to really work with the chain rule to get all the details to work out. So please be aware of that. And but they're doable. Okay. Ask questions if you need to. That's kind of the setup for doing these things in class, is to be able to ask a bunch of questions. But I will see you all in class.